This all stemmed from me like going down the rabbit hole, and I thought I had that Lambda figured out. And then you kind of explained to me that that was actually just a site like Einstein's term for what he was calling the cosmological constant, which I didn't know. But what was crazy, it was kind of a political maneuver, wasn't it?
Well, let's see. I don't know if you could say that. I never saw him as political. I mean, he's up there with my greatest heroes, Johnny Wheeler and Johnny Cash.
David Lee Roth, who was one of the early discoverers. No, I'm just kidding.
Oh, man. Well, let's see. He kind of just did it on his own. You know, Einstein was known for being the lone rider. Now, there could be something to what you're saying.
I mean,
because he did face some opposition when he came out with the theory of relativity by saying time is relative. He would get skeptics in the media, some conservatives and traditionalists didn't agree with it. You even had skepticism in the physics community at first.
yeah.
So he was brave to put out the theory of relativity, but maybe he didn't want to face all that criticism again. He was new to the cosmological community. So he might have felt some peer pressure.
Yeah.
And, you know, he might have even thought, gosh, I might face cancel culture.
You know, much like Galileo and the Catholic Church.
Like, you mean being ostracized maybe in the press and the scientific community? That might be the equivalent he would have faced, huh?
Yes. Like he kept it to himself, didn't he?
You know, Rob, you may have a point there. He had driven a beautiful equation, and he told a few colleagues how ugly he thought it looked with the cosmological constant added on. But he didn't tell the media.
Wow.
But the job of a theoretician is to model what the observations see.
Right?
So I wouldn't call it political.
Really, am I wrong in saying that the James Webb is contesting the cold dark matter model?
Oh yeah, I know what you're talking about, Rob. The James Webb telescope started to see what looked like mature galaxies in the early universe. But we're not even really sure if they are galaxies. Right now they're called candidate galaxies. The distances where they appear may have been overestimated.
Yeah.
There might have been problems with the observation, interpretation, or analysis of the data.
Okay, yeah.
Or we need to revise the models of how galaxies form.
But it's really contested, you know?
Yeah, you're right. And see, there's many other issues and challenges on top of this early universe surprises.
Oh.
It can't explain the nature of dark matter and dark energy. And also, there's the Hubble tension. When we calculate Hubble's constant from early universe data, like the microwave background, it doesn't match the rate that we get from measuring the modern universe. So this is puzzling.
Right. Okay. Yeah. But it's amazing to me how much this stuff is just like throwing darts at a dartboard. Like,
Oh, yeah, I guess that's the process of doing science. You know, you have all these hypotheses and you try them out. They're not all going to hit the bullseye. Trial and error. Learn what works and what doesn't work.
okay.
So we are going methodically through hashing out a lot of the issues.
Now, growing up, born in 1970, I just thought that like the standard model was pretty much the way it is, and we're going to figure it out. Like there was no talk of maybe changing it.
Oh, a well-known constant in cosmology is change itself.
Dots, huh?
Aristotle said that we were at the center of the universe and everything revolves around the earth. And everyone was happy for such a long time until Galileo looked into an early telescope and saw that the Copernican model was correct, that we weren't the center of the universe, the sun was. He published his findings, and what did he get? House arrest for the rest of his life. And then, Newton, he had the universal law of gravity. And he said that we have a static universe. Everyone loved it. That's what they saw for a long time. But along comes Hubble with an even better and better telescopes and notices that no, the universe is expanding and it's not static. So Einstein and everyone shelved the Lambda idea for a while. And in 1998, they notice not only is the universe expanding, but it's expanding at an accelerating rate, which brought in the Lambda CDM standard model. And then they start building space-based telescopes, and they started seeing mature galaxies in the early universe with the James Webb Telescope. And that's one of the things causing this new schism and these new theories and ideas.
Wow.
The only thing that stays the same forever in science is change itself.
Good point.
Do you think that maybe like the whole idea of the Lambda CDM model has been kind of propped up on legs that aren't completely solid on a poor foundation, and maybe like there's about to be some real changes?
Well, there have been proposals for revisions to the standard model, but the standard model matches observations way more than any other model. Other theories tend to be a specialty theory for one aspect of the universe.
Okay. Right. With the explosion of lambda theories over the last 20 years, do some theorists use lambda as a variable?
Well, that's a good question, Rob.
Great.
What is lambda, and why do we even need it?
Yeah, but yes, that's the question.
Well,
Today, 110 years ago,
Oh, God.
Einstein published his field equations for general relativity.
and a few years later, he applied this to the universe. And he found that he needed to put lambda as an extra term in his field equations. He made lambda a constant
Like Sneetches.
to account for what we now call the constant density of dark energy.
Ah.
And since then, lambda has always been a constant.
Okay.
Now, some have developed quintessence models, and they propose a dynamic dark energy.
Alright.
Quintessence shines when we're talking about large scales and recent times in the universe. And it's great at explaining the observed acceleration of the universe without using a constant dark energy. So if we interpret this in terms of the cosmological constant, then this theory is claiming that the quantity which lambda represents, dark energy and dark matter, is not constant. Now, of course, they don't use the symbol lambda to represent this. An interesting historical fact about dark matter is that Vera Rubin found evidence for dark matter by looking at the rotation curves of galaxies. She saw that the outer stars in galaxies were moving faster than they should if we only are considering visible matter. This meant that there had to be some unseen mass, which we now call dark matter. Paul Steinhardt wrote a paper in 1995 suggesting that we have a variable dark energy.
Do you think there's other cosmological theories that have a value, and maybe some have more value than others, or should be weighted more in terms of research than others?
Well, I'm not too sure about that. I do know the foundations and institutions that offer the funding are very meticulous and thorough, basing funding on the reputation of the groups, how important the research is, being sure that the research group has the proper resources, and they spread it across the board. An amount goes even to alternative models.
What are those? Are there cosmological theories that don't use lambda?
Yeah, there's quite a few, and they're really interesting. Giuseppe's over there signaling us that the dark wave, dark coffee is ready.
Thanks, Brian. So I'm gonna go to a commercial. Thanks for giving me those opinions, and I'm gonna have another round with you when we come back.
Thanks.
When we return to the Darkwave podcast, Professor Diederich will discuss alternative models of cosmology.